am Dr. M. Amuda, Associate Professor of Chemistry, V.V. Vanniyaperumal College for Women, Virudhunagar. In this video session, generally all the organic compounds are having proton and carbon. Suppose if you are provided a chemical compound, we are asking you to identify the structure of those compounds. How do you identify? For these questions, you may get the answer by using the nuclear magnetic resonance spectroscopy. Okay, after completion of this session, you may understand the basic concepts of NMR, then NMR active and inactive nuclei, as well as NMR signals for various organic compounds. Thus, you may identify the particular compound and you may tell the answer for our questions. Okay, first of all, you should know the electromagnetic spectrum. This is the radio wave region. In this radio wave region, otherwise called as NMR region, NMR means nuclear magnetic resonance spectroscopy. Here, all the protons and carbon, that means NMR active components, absorb the frequency and show a peak and produce a spectrum. By using this spectrum in the range of 40 to 900 megahertz, we can get a peaks. By analyzing these peaks, we may get a knowledge about the given organic sample. Okay, all the elements should not active in this NMR spectrum. Only the elements which possess the odd atomic number as well as odd mass number as well as half integer spin quantum number, only NMR active compounds. For example, H1, C13, F19, P31 are NMR active. Other components should not give the peak in this region. What is the main use of this nuclear magnetic resonance spectroscopy is to identify the types as well as number of protons which are present in that given organic compound. Okay, what is the mechanism? Suppose if we take if you are provided a particular unknown sample, you should put a sample in the magnetic field. First of all, you should put a applied magnetic field in the NMR region, that means in this radio wave region. Then you apply our given sample in this applied magnetic field. In the sample, all the protons are acting as a tiny magnet. At that time, there are two magnetic fields are produced. That is applied magnetic field and the tiny induced magnetic field. That protons starts to rotate as a top. At that time, that protons absorb the NMR region and produce a peaks. That peaks are analyzed and we may gain a knowledge about that organic compounds. This is the basic mechanism of the NMR spectroscopy. This is the NMR spectrum. For this NMR spectrum, tetramethylsilane is taken as a standard reference compound. Nearer to this standard reference, the field is called as up field. Far away from the TMS is called as down field. Here 0 to 12 is mentioned in x-axis, that is chemical shift value, that is del value. The unit of del value is ppm. In y-axis, peak intensity is showed. Here, suppose if a compound, for example, if we take acetone, for acetone 6 protons are there. If you are provided acetone, you may analyze. There are two types of, that is CH3, two compounds are present and possess 6 protons. But in NMR spectrum, you are getting single peak, that is chemically shifted from TMS to 2.3 range. So, all the 6 protons show a single peak. That means all these 6 protons are chemically equivalent, environmentally equivalent, electronically equivalent. That's why it shows a single peak. Okay, what is chemical shift? The difference between the distance of frequency range, that means it is how much it is shifted from the TMS. The peak is how much far away from the TMS is called as chemical shift. Okay, why should we take tetramethylsilane as a standard one? Because there are 12 protons are there. All the 12 protons are shielded, and nature of that proton that is present in TMS in compared to the other protons of most of the organic compounds. It is chemically inert. That means it does not react with the given sample and miscible with a large range of solvents. It does not take part in intermolecular association with the sample also. Due to the volatile nature of TMS, it is taken as a standard reference for NMR spectroscopy. Okay, in all the organic compounds, there are two types of protons. One is chemically equivalent, another one type is chemically non-equivalent. What is chemically non-equivalent proton? Proton having different chemical environment, different electronic environment. Set of non-equivalent protons show different absorption signals in the NMR region, different chemical shift, different field strength, and also absorbed at different frequency. Such type of protons are called as non-equivalent protons. Let us consider these molecules. For example, if we take the benzene, in benzene there are 6 protons, but it shows only one peak because all the 6 protons are chemically equivalent, environmentally equivalent, and electronically equivalent. So it shows single peak. Let us consider the tetramethylsilane. It also shows a single peak. Then tetramethyl carbon, it shows a single peak. Here this is cyclohexane. All the 12 protons are in single peak. For acetone, single peak. This compound, single peak. Dioxane, it also shows a single peak at 3.7 chemical shift value. For nitromethane, CH3, 3 protons but show a single peak. For this compound, single peak. For unsaturated compound, both the protons are chemically, environmentally, and electronically equivalent with this cis 2 chlorine atoms. So these 2 protons show a single peak. Like this, all the protons are different numbers but show a single peak. Such type of protons are called as equivalent protons. Okay, let us see the, here you see this chloroacetic acid. Here OH group, this OH proton is different chemically environment. That means it is directly attached with O group. Here these 2 protons are different because these 2 are chemically and electronically different with this OH proton. This is directly linked with chlorine and C. So these 2 show a single peak. OH proton, this proton show a another peak. So we are getting 2 peaks apart from tetramethylsilane. So we are getting 2 peaks. So we may conclude that suppose this this compound is given as a to be analyzed compound. This show 2 peaks. So we may be concluded that there are 2 types of protons are present in this compound. Here there are 2 types of protons. Here this 3 protons, CH3 protons are directly linked with O. Here 3 CH3 protons are directly linked with CO. So these 2 are chemically different, environmentally different, electronically different. So we may expect 2 types of signals. Here there are 3 types of protons. CH2 is directly linked with chlorine. CH is directly linked with CH2. In this side there are 2 CH3. 2 CH3 are different. CH is different. CH2 is different. All are protons but are different environment. So we may get the 3 signals. For this compound also 3 signals. For this compound CH3, here CH2Cl. These CH3 are one type. This CH2 is directly linked with chlorine. So this is another type. So we may get the 2 types of signals. Here CH2, CH2, Cl, Cl. These 2, there are 4 protons but chemically 4 protons are chemically environmentally equal. So we are getting single signal, NMR signal. Here 3 types of protons because CH2 is linked with bromine. Here CH2 is linked with chlorine. So CH2 is directly linked with the CH2. So there are 3 types of protons, 3 NMR signals. Here 2 types of protons, 2 NMR signals. Here for ethanol, CH3 is different, CH2 is different, OH is different. So 3 types of protons, 3 NMR signals. For unsaturated compound, cis and trans isomer play a vital role. These 2 protons are cis with bromine atom, so we are getting single peak. This 2 protons are trans with same bromine atom, so we are getting single peak. But for here, this proton is cis with OCH3, this proton is cis with bromine. So we are getting 2 peaks. For this compound, unsaturated compound, CH3, H are trans position. So we are getting these two are same type, CH3 are same type. We are getting 2 types of protons and 2 types of signals. Here also CH single proton, and we are getting same single signal. Here you see this is directly electronically related with chlorine. This proton is electronically related with bromine. So we are getting 2 signals and 2 types of protons. Here there are 3 types of protons. This proton is directly linked with chlorine. This is directly linked with this hydrogen. Then this proton is linked with this A type. So we are getting the 3 signals. These 3 are chemically different, environmentally different, electronically different. Thus we may identify the cis and trans isomer by using this NMR spectra. Then let us consider aromatic compounds. For aromatic compounds, ortho and para directing groups and ortho and para substitution play a vital role. Here all the protons of benzene show a single peak. But for this compound, these 2 protons are chemically related with the fluorine as well as chlorine. So it show a single peak. Here these 2 protons are ortho substituted to fluorine, ortho substituted to fluorine, para substituted to chlorine. So these 2 are in same environment region, that is equivalent proton, and show a single peak. But for this compound, these 2 protons are ortho substituted to nitro group and para substituted to proton. But these 2 protons are ortho substituted to bromine and para substituted to proton. So these 2 are different environment. These 2 are in chemically different environment. So we are getting 2 peaks, and we may identify 2 types of protons are there. For this compound, these 2 protons are different. This proton is different. These 2 are ortho substituted to this bromine. Here this proton is para substituted this bromine atom. So these 3 are two different compounds and show a 2 peaks in that NMR spectrum. Thus by using this NMR spectrum, we may identify the number of protons as well as the types of protons, whether it is chemically equivalent or non-equivalent, by using this NMR spectrum. Okay girls, we will see in the next video. Thank you.